Hello, good afternoon, and so welcome to Lab 2. So am I audible first of all?
Yes.
Cool, thanks.
Yes,
Okay, so in the last lab, we covered a few basic things about how to make a neural network, optimizers and losses and all. But then we didn't get a chance to actually train the network on the dataset that we were using. So the agenda for today will be first of all to complete that, to write a training script and train it for a few number of epochs and see what happens. And then we'll also uh, train on the same dataset, but then instead of using a simple neural network, we'll use a convolutional neural network. And then you can compare between the two um, to see the difference. Okay, so last time, so just a basic recap, we uh, we were using the MNIST dataset. We created training and testing splits. So the train split had 1,000 images and test split had 500 images. And then, so we took each of the image and then we reshaped it. So we used the view function, we reshaped it so that it's a single flat tensor of size 784. And the same thing for validation as well. And we have the corresponding labels in train Y and validation Y. And then we made a model. We made a classification model and we implemented it in the form of class. And this model takes in our images or flattened tensors and it returns a tensor of size 10, where 10 is the number of classes that we require. So in our output, because there are 10 labels from 0 to 9, we have 10 classes. So the output is a tensor of size 10. And so we made a classifier object, so with 512 hidden units, which just means there are 512 hidden units in the single hidden layer. And we chose a loss and we chose an optimizer. So I told you the loss is just a metric which helps us to uh, which helps the model to judge whether its output is good or not. And then the optimizer, this is the actual optimization algorithm that we're using, and it works on the model parameters. So it actually modifies the weights of the model so that it can optimize the loss. So yeah, so this is where we stopped last time, I think. And yes, so we divided both the training and validation data by 255 because so usually so the data is from 0 to 255. Each of the pixels, the value is from 0 to 255. So we divided by the data by 255 so that now it will be between 0 and 1. And I was talking about this last time, how it's a good idea to normalize your data before passing it to your model. And then we specified a few hyperparameters. So batch size means how many images you're passing at once through your GPU or through your model. So how many images do you pass at once through your model? That is called batch size. And a single batch size worth of images is called, so when you're done with a single batch, it's called an iteration. And the number of epochs is how many times you're going over the whole data set. So it's not sufficient to pass your entire data to the model just once. You'll have to pass it multiple times. So how many times you're actually going over the entire data set, it's called an epoch. And the number of epochs that you're doing here is 200. And this is not a fixed number. You'll have to play around with this and decide for yourself. Okay. So now we can actually write the actual training script, which will take out data that we have prepared. It will pass our data to the model. It will calculate the loss, and then it will do backpropagation, which means it will calculate the gradients, and then it will use the optimizer. It will use the optimization algorithm to do one step of optimization at the for each pass through the model. Okay. So let's see. So let me first. Okay, it's already GPU. Hopefully we get a GPU this time. Last time we did not get a GPU instance, so this time we'll actually require it. Okay. Um, so let me run. Firstly, we need torch. Mm, okay. So a few more things that we can use. Um, so wait, I'll just create a new. So for training, you'll be training it for these many epochs. So first thing you can do is you can make a for loop which iterates over each epoch. So you can do for so, okay, and then let's have a variable which will accumulate all the losses for that single epoch. So we'll just say epoch loss 0. Okay, and so one thing that you have to do is, so if you need gradients to be computed, then you have to set your model to train mode. Later on, when you're doing evaluation, that is when you're actually evaluating your trained model on test data or on your validation data, then you have to switch it to eval mode. So you do model.eval, then gradients are not computed. So when you're actually doing evaluation, you do not want gradients to be computed, because then it's a loss of computing resources, because you do not actually have to, you're actually not doing training at that point, you're only doing evaluation. So just keep this in mind, and there'll also be a few other changes to some kind of layers, like some kinds of normalization. There'll be like certain differences, but then the main difference is that gradients won't be computed. So um, yeah, so remember to switch it to train model dot, I mean, remember to do model dot train before you actually go ahead with training a model. Okay, so for each epoch, what do we have to do? So we have to pass all the data through the model. So we do that in fixed batches. So we'll take first batch and we'll pass through the model, and then we'll take the second batch and we'll pass it through the model. So we have to iterate over not just the epochs, but also the batches inside each epoch. So what we can do is we can create a variable here, and we can say number of batches per training epoch. And how do we get this? We have the uh, trainets, which is the training data. So you can say trainets dot shape. So this will give you the shape of the trainets tensor. But then trainets tensor is number of images times 784, which is the size of each image. So we want just the first dimension, which tells you how many images are there, and then we'll divide this by the batch size. So what is happening here is you're taking the total number of images and you're dividing it by the batch size, which will give you number of batches in each epoch. And similarly, you can do the same thing for you'll need the same thing for validation as well. So you can say number of batches for validation is validation. It's just a second, actually, and you can divide it by batch size. Okay. So if you want to see what the actual value is now, so number of batches per train, yes. So you can see 10. So why is it 10? Because your dataset is of size 1000 and you have 100 is your batch size. So obviously there'll be 10 batches per epoch. Yes,
So why are we taking only 1,000 images and why not the entire
you
data
can take
set?
the entire dataset, but then, I mean, this is for demonstration purposes, right? When you actually do it, you can use how much ever data you want.
Okay.
Yeah. I mean, there's no particular reason. So, I mean, later when we're training a CNN, I'll probably use more data. But for this, it's pretty much, I mean, 1000 images is more than enough just to see it working.
All right.
Yeah. Um, okay. So number of batches for training epoch is 10, which means that there are 10 batches per epoch. So you can iterate over the batches in every epoch as well. So you can say for batch index in Okay. What you'll do is, so what is the input that we're going to pass to our model? So the input will be train it, but then, so what we have to do is we have to take that specific batch from the data set. So because here we are not doing any kind of shuffling, we can just directly index into the tensor and just use the batches like as it is. So for batch index, we can say batch index size 2. Okay, so what is happening here? You are taking a single batch of images, and which images you're choosing will depend upon the batch index. And so this is pretty self-explanatory. So if anybody has a doubt, just ask. Like, it's pretty self-explanatory, right? You're just choosing the batch corresponding to that batch index. And how do you do that? You go from batch index times batch size to batch index plus 1 times batch size. So you'll have batch index number of images now. This is just simply simple indexing. So you have your input, and how do you get your output? You take your input and pass it through the model. I think we named it model. Let's see what we named our classifier. Yeah, we called it model. So you take your input images, and you pass it through the model. So you'll get your output. You also, you need the actual output that your model gave you, and you also need the actual labels, the correct labels also. Only then you can compute loss. So the actual targets will be, where do you get that from? You get that from train Y and the same indexing. Okay. Okay. So now you have the output, you have the targets. So now what can you do with this? You can calculate the loss. And again, loss also we have already declared it. We are using the cross entropy loss. So this specifically, there are many kinds of losses, and for classification, this is a loss that we usually use. And Sir will teach this in the class. I don't think he has covered it yet. I'm not sure if he has covered it yet or not. So just know that this is a means of calculating a metric which will tell the model how good your output is. So for that, you need the actual output. You also need the targets, which are the actual labels. And so you can calculate the loss for that batch. So you can say batch loss is loss, and to the loss you can pass in your output and the targets. Okay, so now you have your loss. And to calculate gradients, if you remember last time when we were discussing AutoGrad, I told you how we calculate gradients. So you go batch loss dot backward. So now the entire computational map, all the gradients in all the steps will be computed by PyTorch automatically. You do not have to do anything. Okay. So now you have calculated all the gradients. Now, once you have calculated the gradients, what are you going to do? So you're going to use your gradient based optimizer, whatever optimizer you're using. You want that optimizer to optimize the weights. So how you do that is you go optimizer dot step. So when you do this, what happens is the optimizer, which you have declared here, which is stochastic gradient descent, SGD, you use this optimizer. The optimizer, you have passed the parameters of the model, and there's another hyperparameter called learning rate, which is not important right now. So you have this optimizer which has access to the weights of the model, and you also have calculated the gradients corresponding to all the computations that the model has done. So now what you can do is, when you do optimizer.step, what is happening is implicitly the optimizer uses all these gradients, and then it does one step of optimization which will slightly modify the weights of the models based on the learning rate, based on the hyperparameter learning rate. It will slightly modify the weights of the model so that it produces a slightly better output. And when you do this iteratively, when you do this incrementally, it'll slowly give you better and better results. Okay, so I hope this is clear. So what you've done here is, you've just done one single step of optimization using the gradients that you calculated. So to calculate the gradients, you did batch loss dot backward. Okay. So now you can add your batch loss to the epoch loss. So you're keeping track of loss over the entire epoch. So you can just add the batch loss here. So one thing that I forgot was before you start, you have to do optimizer dot zero grad. So what this does is, so once you've taken a step of optimization, so when you're passing the next batch through the model, then you want the gradients to be calculated fresh. You do not want to accumulate the gradients from the last time, from the last calculation, uh, from the last forward pass. So imagine you're taking the first batch, you're passing it to the model, you get your input and output, and you calculate your loss, and you calculate all the gradients, and you do one step of optimization. Now, for your next batch, when you're doing all these steps for the next batch, then you do not want to use the gradients from the last batch. You want to calculate gradients afresh. So what so before you start doing all of the computation, what you have to do is within each batch you should say optimizer dot zero grad. So that'll zero out all the gradients. Okay. So now what we can do is so let's say so so basically this is it. So after we run this, the model will have trained for epoch number of epochs. Okay, so in order to visualize what's happening, it's a good idea to keep track of the loss. What happens to the loss after each epoch, and if it's going down, that's usually a good indicator. That's not the only thing that you should be looking at, but your goal is to decrease loss during training. The goal of your optimizer is to make your loss as small as possible, and so you have to see if that's actually happening with your training script. So to do that, it's a good idea to keep track of the losses at each epoch. So what we'll do is we'll make a list. uh, we'll call it loss at each epoch. Okay, so list. And what we'll do is after each epoch, so after each epoch is done, what we'll do is we'll just append the loss for that single epoch to this list so that we can keep track. So we'll say at each epoch. So we'll add the epoch loss to it. Okay. Cool. So this is the basic training script. So we'll add a few extra functionality so that we can visualize what's going on. So you've calculated the loss at each epoch, but then maybe you also want to see how good your model is actually performing on new data that it hasn't seen before. So here you are just reporting the training loss. So maybe you can also report the validation loss. So you can report the loss on the validation uh, data that you've created. So what you can do is you can have another for loop within the epoch loop. You can have another for loop, and you can say for uh, again we will have an input which will be just validation. I should have just copy pasted it. Let me just copy paste this. It's the same thing, but here you're doing it for number of batches validation, number of batches instead of number of training batches. And you get your output by passing your model, passing the input through the model, and your output will be validation y of same thing. Okay. So how do you report your performance of your model after each epoch? So you've trained for one epoch, and now you want to know how good your model is. So one thing that you can do is you can calculate loss, but then when you're doing it for new data that the model has not seen, then it's usually a good idea to report it in the form of accuracy or something that humans can understand. So when you say your model after these many epochs of training, it's it's giving you 60% 60% accuracy, then it's intuitive for you to understand it. So you can say, oh, after these many epochs of training, my model is giving me this much performance in terms of accuracy. If you say loss, it's fine, but then okay, so but then accuracy is you can visualize accuracy better. So let's do one thing. Let's create a function which calculates accuracy, and then we can call that within the training loop. So we can calculate the accuracy after each epoch. So let's have a function called get accuracy. And what this function does is it takes in your predictions and it takes in your targets, and it will tell you how good your prediction is. So it will tell you how good your prediction is, but not in terms of loss, but rather in terms of the actual accuracy of your model. Okay, so how do you calculate accuracy? You calculate accuracy by total number of correct predictions divided by total number of predictions times 100. So your total number of predictions will be the length of predictions. Okay, and you also need a uh, you also need to keep track of how many correct predictions are there. So if predictions then you can just do okay, so I hope this is clear. It's pretty straightforward function. So what you're doing is you're taking in your predictions and your targets, and how do you calculate accuracy? You calculate accuracy by total correct by total number of samples times 100. So your total number of samples is length. You get that by calling len on predictions, and or you can call it on targets also. It will be the same. And you keep track of how many are actually correct in this variable correct, and you iterate over the entire length of the predictions. You look at each prediction and you ask, oh, is it same as targets? If it's same as targets, then you increment the correct variable. So finally, after this is done, what will correct have? Correct will have the actual number of samples for which your model predicted correctly. And so you divide that by the total length and you multiply it by 100, you get the accuracy. It's pretty straightforward, it's a simple function. Okay, so now that you have, so for a validation, so let me just add a few comments so that you're not confused. So validation or reporting, validation accuracy. Okay. Now, the output of the model. So you're taking your batch and you're passing it through your model, and you get some output. So, but the output is not in terms of labels right now. So it's in terms of numbers. You have a tensor of size 10, and this tensor has numbers in it. So there'll be scores. You can think of it as scores. So there'll be a number. There'll be 10 numbers, and each of these numbers correspond to a kind of a score to for each of the classes. So there'll be the first number will correspond to the first class, which is 0. Second number will correspond to the second class, which is 1, and so on. And how do you decide what your model is actually predicting? So you'll decide what your model is actually predicting by taking the index corresponding to the maximum uh, value. So in your tensor, you'll have 10 values, and you'll look at the tensor and you'll say which index has the maximum value. So let's say it's at the third index, and so then you'll understand that your model is saying, with maximum probability, I'm predicting that this image contains 3 or this image contains 4. And so how do you get that prediction, the actual prediction of your model, which corresponds to the class? How do you get that from your output? So you can just do there's this function in torch called argmaths, and so you can call the argmaths function on output. So what this does is, wait, I'll give you an example, that'll be easier. Okay, so let's say we have a tensor T1. Let's say this is a 1 by 10 tensor. Okay, so we have a tensor with different values in it. This will be similar to the output of your model. So your model also returns a tensor of size 10, and this tensor also has values which corresponds to each class. And if you call torch.argmaths on this function, or on this tensor T1, and along which dimension do you want to calculate argmaths? So it's in this case it's 0. Okay. Okay, that's not what I meant to do. Let's just call torch. Right. So the maximum value is 0.9509. And what is the index corresponding to this value? It is 0, 1, 2. And what argmaths does is, it does not return the maximum value, it returns the index corresponding to the maximum value. So imagine you pass an image which contains the digit 3. You pass it through your model, and you get an output which is a tensor of size 10, similar to this. And now, how do you tell that your model is actually saying this image contains a 3? You'll take this tensor and you'll say, okay, which index has the maximum value? Which index has the maximum value? In this case, it was 2. And if our image had a 3 in it, so we hope that the third index would have the maximum value. So when you call torch.argmaths, what essentially happens is, it takes the tensor, it looks which index has the maximum value, and it returns the index. It does not return the value, it returns the index corresponding to the maximum value. And so that's what we're doing here. In our case, so this dim equal to 1, what this does is, in our case, the output, what will be the dimensions of the output? The dimensions of the output will be of size, batch size times 10. It will be a tensor of size, batch size times 10, because you're not just passing a single image, you're passing batch size number of images through the model, and so your output will be of size batch size times 10. And you want to calculate the argmaths along which dimension? You do not want to calculate the argmaths along the batch size dimension. You want to calculate the argmaths along the dimension of the actual tensor, of the actual individual tensors corresponding to the individual images. Yes.
So, could you please explain the prediction, the argmax part once again?
Yes.
What I understood is that we're using the validation set to find the accuracy of the model.
Yes. After each
So,
epoch.
so we took validation X.
Validation X
Where is
has 500 images, and we are selecting the specific batch out of these 500 images, and then we're passing it through the model. And so what will we get from the model? We'll get, so each corresponding to each image, there will be a tensor of size 10, and because we are passing batch size number of images, we'll get batch size times batch size comma 10 size tensor. This will be the shape of the tensor that you're getting as output.
batch size comma 10 by the number of batches size 10 comma 10.
So what is the shape of this tensor input?
Batch size is the number of images.
Batch size is the number of images that you're passing in this single iteration.
So okay, so for each batch
Yeah,
size.
for batch index. So batch index corresponds to each batch. So
Okay,
in our case, because there are 10 batches per epoch, or for validation, it will be 5, because 500 images and batch size of 100, there'll be 5 batches per epoch. And so when you're doing, so batch index will go from 0 to 4.
Okay, so we have an output
Output which
matrix
corresponds to a single batch, and this, so it will be of size batch size comma 10.
and
Because
target output also, sorry.
target output, yes, target output will also be of same size, will also be of the same shape.
Okay. And what does argmax do?
Okay, so you got the output from your model, but then the output is in the form of a tensor of size 10, and from this you want to get the corresponding label. So what is the output of a model? The output of a model is of size, so corresponding to each image, there will be a tensor of size 10. But then in order to actually calculate accuracy, then you have to get what the model is actually predicting in terms of label. Is your model saying that it's a 3 in this image? Is your model saying that it's a 4 in this image? You actually need that information to calculate accuracy, right? So
I mean, in the get accuracy function,
yes,
we had predictions and target.
yes.
So target was the target is this.
Target is the actual label. So target will be 0, 1, 2, 3, corresponding to what the actual image is, what the actual image had. And
So
predictions
prediction.
will be what we are saying, what the model is saying. Oh, is the model saying that it's 1? Is the model saying it's 2?
So predictions and targets are both 1D vectors.
Predictions and targets. So in this case, so here the predictions and targets are what we are passing to the get accuracy model, get accuracy function. And in this case, so what I'm going to do is, so I got these predictions right, and now I'm going to pass these predictions and this target out to get accuracy, and then get accuracy will tell me what the actual accuracy is. If I passed out the actual output of the model to get accuracy, that does not make sense, because the output is for each image the output is of size 10, and we do not want to pass 10 numbers. We want to we want to calculate the accuracy based on what the model is predicting in terms of the label. Is the model saying that it's a 3 in this image? Is the model saying it's a 4 in this image? You need that information. You do not need the actual scores corresponding to each label. Yes, yes,
Sir, why are we not using like in the neural network while we were making it?
yes.
We could have used like the softmax function, and we would have avoided having to make a new variable of prediction, because the output then would have been one value.
If you use softmax, then the output will still be of size 10, but then it will correspond to probabilities between 0 and 1.
Sorry, yes. So I meant then we can find out the maximum
Yes, you
one.
can do
Like,
that.
why are we using argmax? Like, is there a special? Malab, is it better in some case?
Um, so in our model, let's go back to the model. In our model, the last layer is a linear layer. So which means that your output can be from minus infinity to infinity. Right. So it's a score. It can be positive, it can be negative, it can be 0. It's a score. So you could have added a softmax here. But then the reason I did not do that is just to keep it simple, because for our loss, we were using cross entropy, right? So let me just show you cross entropy. Yes. So this is what we were using. So here you can say, here you can see, the input is expected to contain raw unnormalized scores for each class. It does not say that you have to normalize it. Raw unnormalized means that you should not apply softmax before you pass through it. Pass it to the loss,
Okay.
right? Because the way the cross entropy class is implemented in PyTorch, it will automatically take care of that for you. You should pass the actual raw unnormalized scores corresponding to each class to the loss, and you should not pass it after softmax. And because we are using this implementation of cross entropy loss, that is why I did not use the softmax there.
Okay.
Right. So you understand, right? It's very simple. What does your output have? Your output has scores, 10 scores corresponding to each label. It will have a score corresponding to 0, a score corresponding to 1, a score corresponding to 2, and so on. But then you can't use that information to calculate accuracy. What do you need? You need, corresponding to each image, you need a label which says what is your model actually predicting. Is it predicting whether it's 0? Is it predicting whether it's 1, and so on? And how do you get that? So you take your output and you look across all the 10 numbers and you say at which index is there a maximum value. So if there's a maximum value at index 3, then that means your model is predicting 3, or that's how you're interpreting it. Your model is predicting 3. And so how do you get that information? So you do an argmax. So what argmax does is, you know what maths is. If you do torch.maths, then that will give you the actual maximum value. but then you do not need the actual maximum value. You need the index corresponding to that maximum value. You need to get the information which says that which index has the maximum value, which label has the corresponding maximum value. So you get that. For that specific reason, you use the argmax function, and you pass output through the your argmax, and you use dim equal to 1 because you want to calculate the argmax for this dimension, not across batch size. Across these 10 numbers you want to calculate argmax. So now what will predictions have? Predictions will have a tensor which is of size batch size comma 1. Yes. Yes.
Just one confirmation.
Yes.
Then that means that if our the Pred's variable, that is a vector. That is a vector of number of values batch size.
Batch size. Yes.
So that means the target that is also a vector only, na? 500 into 1. Say, I mean batch size into 1.
Which one?
Target out should also be batch size comma 1. Na?
Yeah. Right. Okay. Thanks.
That was my confusion. Okay. Thank you.
Yeah. Cool. Yeah. Thanks. Yeah, I just copied and pasted this, so it'll be batch size comma 1 because there'll be only a single label corresponding to each batch, so corresponding to each image. Cool, that's nice. Yes.
Actually, while calculating the loss, we are not taking the labels, we are taking the actual probability.
So not the probability, the actual scores that you are getting for each. The actual numbers, whatever your model is outputting, you pass that to cross entropy because that's how it's implemented.
So basically, we want to see how big the actual number is, the true label which is there corresponding to that value, how big that is, and how small the other numbers are.
Yes, that will
like
be
if, for example,
implicitly. So when you're optimizing using your optimizer, you're doing some kind of optimization, right? So and you're doing the optimization so that you're minimizing the loss. And so when you're minimizing the loss, all of this will implicitly happen. All this that you're talking about the other scores being lower and that single score being the maximum, all of this will implicitly happen.
Okay.
Because that is our goal, right? We want our model to predict good predictions. And so when you're using this, so when you're doing optimization, the weights of the model will be adjusted so that all of these results that you want will implicitly happen.
Okay, thank you.
Okay, so we have the predictions. So what we'll do is we'll create a list for the predictions and targets, so then we can finally pass it through the, so we'll call it, we'll have train predictions list, and we'll also have a target list. Okay, this is not for training, this is validation. Validation, predictions, and validation targets. Okay, and then to this we'll of our predictions. So currently our predictions are tensors. So what we'll do, we'll convert them to numpy arrays. So we can just do dot numpy. So I hope you understood what happened here. So the predictions that you finally got. So predictions will be what? Predictions will be a tensor because it's an output of a torch function. It's a tensor, and it has the labels corresponding to the each image that your model has predicted. And I'm just appending it to a list so that finally after everything is done, you can pass all of your predictions and all of your targets to the accuracy function, get accuracy function, and then it will calculate accuracy for you. And similarly, you also keep track of your targets. Target out. Okay, and once your entire loop is done, which means that once you have gone over all the batches, what you'll do is then you can so again let's create another list, and let's call it validation accuracy something. So okay, so let me explain what happened. So we calculated the predictions for each batch, and then we added it to a list. So this list will after the entire loop has run. Okay, this is not supposed to be here. Yeah, it's supposed to be here. Okay, after the entire loop has run, what will val predictions have? Val predictions will have the predictions corresponding to all the images in the validation set, and val targets will have the targets corresponding to each image in the all the images in the validation set. And now you have two numpy arrays and corresponding to predictions and targets, and then you can just pass it through the get accuracy function that we wrote. You can pass the predictions and the targets to the get accuracy function, and it will calculate your accuracy. And then you also have to keep track of your accuracy. So you do that by appending it to another list. So an outer list. So this I created a list outside the epoch for loop, and I called it validation accuracies. And this will keep track of the validation accuracy after each epoch, which you calculate inside the loop here. Okay. Is there anything that's not clear here? Because okay, I'm assuming it's clear. Now, okay. So if you want, you can actually also keep track of training accuracy. So uh, you can do the exact same thing, but also for training, because you can also get an idea of how good your model is performing on your training data also. So you're training your model after each epoch, you can report how good your model is doing on your training data in terms of accuracy. You can report it in terms of loss also. So loss is what the optimizer will be using. But then for humans, it's better to understand in terms of accuracy or other such kind of metrics. So that is why we reported our accuracy on the validation data. So the validation data is data that the model has not seen before. But then you can also report your accuracy on the training data that you actually trained on. So that uh, so it's optional. You can do it. I mean, we can do it because yeah. So we can have a for reporting the training accuracy as well. Um, so let's create another list then called training accuracies. Similar to how we let's put this here. The same thing that we did for validation. We'll be keeping track of the predictions and the targets in a list. Everything else will be exact same thing. Let's copy paste this. And your predictions will be again argmaths, tortured argmaths over there. No, preds. Just a second, just a second. I'll just fill in the code so that then I can explain what's happening. And it's pretty much it, I guess. So then you have your train targets. You can do the same thing here. I think I called it train. Okay, so let me just explain this and then I'll come to your question. So it's like exactly the same thing as we did for validation accuracy, we're doing for your training accuracy as well. So instead of passing your validation, instead of calculating the accuracy on your validation set, you're calculating accuracy on your training set. So you take your train model after this epoch. So you've done all this training step for the single epoch, and so you take that model with with the updated weights. You pass each batch through the model, and you calculate the prediction, the output, and then you also get predictions like we did for validation using the argmaths, which will give you the actual labels corresponding to the output, corresponding to the image that your model is predicting. And then you also have the ground truth targets, and then you keep track of both in a list. You just add it to a list, and finally you do the exact same thing. You calculate the accuracy using the get accuracy function. You pass train predictions and train targets to it, and this will give you the accuracy corresponding to the training data. And then I'm just adding it to a list so that I can keep track of how the accuracy for the training accuracy is changing with respect to after each epoch. Okay, Srishti, yes.
Uh, in the last code that you wrote, are we actually training the model twice?
No, you're not training the model twice. You're okay. This loop is the training loop. The actual training is happening here in this loop. So here, in the first loop, what is happening? In the first loop, you're passing all your data through your model. You're getting the output, and then you're calculating the loss here. You're calculating the loss here, which is the loss is what? The loss is the metric that your optimizer will use, and you're using the optimizer to do one optimization step. And after this, the weights of your model will be slightly changed. It will be slightly more optimized after one step of this. And you do this for over all the batches in the epoch. Okay, so now your model has trained for one epoch, and your model will have slightly different weights than before it started. And with this new model, with this new weights of the model, what do you want to do? You can report your accuracy. After one epoch of training, how good is my model doing, and how do you quantify how good your model is doing? You use that using accuracy. And there are two options. You can report your accuracy on your training data set, or you can report your accuracy on your validation data set. The difference is that the training data set your model has seen before. The validation data set it has not seen before. So validation data set will give you a better idea of how actually the model is performing on new data that the model hasn't seen before. And the training accuracy will give you an idea of how good the model is able to fit the data. How well is my model able to learn the data that it's seeing, and that information I'll get from the training accuracy, and the validation accuracy will tell you how good is your model performing on new data that it doesn't never seen before. And you
Right.
report the training accuracy and the validation accuracy after each epoch. So after one epoch of training, your model will have new weights, and with this new weights, is my model getting better, is my model getting worse? You have to report that after each epoch, and
Right.
you report that after each. So this loop, so I think the confusion here was because I copy pasted stuff from here, and you're passing the training data again through the model. You're passing the training data again, but here we haven't calculated the loss. We haven't used the optimizer here. Do you understand?
Yeah.
I like
Yeah.
okay. Um, right. So this is pretty much it. So we have wrote. I think this is more than enough for now. So one thing that I forgot was before training, I switched the model to train mode, and before evaluating, we have to switch it to the eval mode, which I had mentioned earlier, but then I forgot to do it. So once your model is done, so you switch it to train mode, you train your model. Okay, you go over all the data, you do your optimization steps, and now the weights of your model will be different. It will be slightly different. And then you switch your model to eval mode, which means evaluating mode, for so that your gradients need not to be calculated. And then you use this model in evaluation mode, and then you pass your training data again through it, but you're not calculating loss. Here you want to calculate the accuracy of the model on the training data. You also calculate the accuracy of the model on the validation data. And then you keep adding this to a list, so that finally you can see how your model is performing over the course of the entire training, not just for one epoch. You can say, okay, for after 100 epochs, my the training accuracy was this much, the validation accuracy was this much, but after 200 epochs, it improved to so and so. Okay, so what did I do? Yes, okay. So this is a simple training loop, and okay, so one thing that we can do is we can have a print function within for each epoch, so that we can see the result as it's happening instead of after the entire training is done. So usually this is a very small model, so it'll train in the matter of a couple of seconds, because we are only using 1,000 images, right? So it'll be pretty fast. But then in the future, when you're training big models, a single epoch of training might take maybe up to a few hours also. So you do not want to just have your code running and not know what's happening. So what you can do is you can report your loss, you can report your accuracy after each epoch, so that you can print it out. So let's say so epoch, my current epoch is let's say, okay, and then our training loss will be a float. So epoch will tell you what epoch it is right now, and then where are we calculating the losses in this list. So this will tell you what the last loss that we've added is. So after the entire epoch is done, and after we've added the loss corresponding to that epoch, that will be there in this list. So the last element of that will be the loss corresponding to the epoch that we just completed. Similarly, I think we have a list for training accuracies. Uh, okay, let's try running this. Not sure if it'll work. Let's see. Okay, it's done. So we have trained it for 200 epochs. So you can see, so epoch 0, when is this printed? This is printed after it has done one epoch of training. So after it has done one epoch of training, my loss is this much, my training accuracy is this much, and my validation accuracy is this much. Training accuracy is the accuracy of your model on your training data, and this is the accuracy on your validation data. So the numbers, and then you keep training it for 200 epochs, and you can see the loss is continuously decreasing. So the loss started at around 22.97 and it's continuously decreasing throughout the period of training. And your accuracy is also improving. So you started out at 19% accuracy on a training set, and your validation set, and it progressively increases. And finally, after 200 epochs of training, your model has 93% accuracy on your training data, which it has already seen, and 86.2% accuracy on your validation data, which it has never seen before. So that's it. So you've trained your first neural network, and so one thing you can do is you can keep so you can visualize what is happening during training. You can make a graph or something. So let's make a simple plot. Um, so let's import NumPy. I'm not sure if I imported it before. So I'll use matplotlib, which is a library you can use for plotting. Okay, and let's training accuracy. So the actual code here is not important. So what I'm doing is I'm going to plot the training accuracy and the validation accuracy over each epoch. Let's accurate. Okay, yeah, 3C's accuracy and training. Yeah, that's a problem. Training accuracies. Okay, let's just see what happens. Right, so the thing that you see in red is the training accuracy, and the HSATs is here. Okay, let me switch off my HSATs is here is the epoch, and the y-axis corresponds to the accuracy, which goes from 0 to 100. So as you're training, the thing in red, which is your training accuracy, is consistently improving, and the thing in blue, which is your validation accuracy, is also continuously improving, and your training accuracy is higher than your validation accuracy, which should be expected because your model has actually seen your training data, it hasn't seen your validation data, so it will obviously perform better on the training data. Okay, so that is first training a simple neural network. So now we'll look at CNNs, and before that, do you guys have any doubts? Anything at all?
Sir, can you show the print function again once?
What function? This function, print function.
Yes.
Yeah. There's nothing here. I'm just printing out the data after each epoch. So I'm printing the epoch. So epoch will have which epoch it is currently, which goes from 0 to 199. Loss at each epoch is a list that we're keeping track of, where we're appending the loss after each epoch. We are adding to this list, and so the last element of that you can access using -1. Same thing for training accuracies and validation accuracies, which are lists that you're keeping track of. Is there anything else? Okay, so let's do CNNs then. Okay, so I think we have around 50 minutes left, and I mean, there's not much code that we have tried because we can repurpose the training loop that we used here without much changes, because it's the exact same thing. Your CNNs will also give same output. Only difference will be that your model will be different now. Your model will be a CNN based model instead of, so earlier we used a fully connected network, which is a type of neural network. Now we'll use something called a convolutional neural network, or CNN, which typically performs better for images. So for images, you'll see how better it is. And maybe not for MNIST. I'm not sure how much of an improvement it will give for MNIST, but usually for vision, usually for image data or videos, you make use of something called a convolutional neural network, because then fully connected networks don't perform that great for that kind of tasks. So, and in our next lab we'll be looking at something specific to computer vision. So there I'll dive deep into what is actually happening. But right now we'll just make a simple CNN and we'll train it on the exact same data set. Yes, somebody? No? Okay, I thought I heard a...
Can we please have a few minutes of break now? Just 2 or 3 minutes.
Yeah, sure. Cool.
Thank you.
Okay. It's been 2 minutes, right? I don't think we have much time because we still have to write the entire thing. So add a new section, I think. Okay, so most of the stuff will be the exact same. We just have to make a new model now. So let's do that. So earlier when we made a model, we called it classifier. So now we'll name it CNN classifier or something like that. So make a class. We'll call it CNN classifier. And again, because it's implementing a neural network, you have to inherit from this class called nn.module. It's a strict thing. You have to do it every time. And okay, you'll have a self and you'll also have a forward function like before. Okay, so let's first write the init method. Cool. So now what we're gonna do is we are gonna make a CNN model. So in CNN model, you have something called a convolutional layer, and in these convolutional layers, you will be doing operations called convolutions. So in PyTorch, it's implemented as con2d. There's a function there's a class called con2d, and it applies a 2D convolution over an input signal, and this is what you'll be using. So I'll just add in the layers, and then you can. Let's create layers. It's called self.con1. First convolution layer is a con2d, which takes in an image which has one channel because it's a black and white image. It has one channel, and let's say you want the output should be 10. There should be 10 channels in the output, and you have a kernel size. Wait, what happened? Okay. Say the kernel size is 5. Let's try this one. So these are all. So I don't think Sir has taught you convolutional networks so far. I'm not sure. Let me check.
Yes, it does.
Okay, so he's just covered neural networks. Great. So how do I go about this then? So there are in convolutional neural networks there are convolutional layers. So like you had fully connected layers before, nn.linear. You used nn.linear earlier. So similar to that, you have other different kinds of layers. So the whole so there'll be various kinds of layers that you can use in deep learning, and convolutional layers are a specific kind of layers that you can apply. And a 2D convolution, because it's 2D data, it's a 2D image, right? In when you're passing data through your convolutional network, you are not going to flatten it. So earlier, if you remember, you had a 28 by 28 image. You flattened it so that it's a 728 times 28 tensor. So it's a 1 by 784 tensor. You flattened the tensor and then you pass it through your model, because it's a fully connected network. It is a fully connected network then, and that's how you usually do it. But for convolutional networks, you do not flatten your image. You pass it as it is. You pass your image. You pass your 28 by 28 image through it, and these convolutional layers will perform certain operations called convolutions, and it will keep on modifying the image. And these are specific parameters of this operation, of this convolutional operation. So there's something called kernel size, and there's something called stride. So it's convolutional network. Let's Google it. Let me see. Right. So let's say this is your image. Let's say you have 1, 2, 3, 4, 3, 4, 5, 6. So say you have a 6 by 6 image. Okay. And then the data inside a 6 by 6 image won't be zeros and ones. It will be so you have a 6 by 6 image, and what you do is you use a kernel, which is another matrix, which is another tensor, and this matrix will be it might be a 3 by 3 matrix, it might be a 5 by 5 matrix. So in our case, we are using a 5 kernel size of 5, which means that we are using a 5 by 5 matrix, and then you're going to do some operation on this tensor using this kernel. And after you do some operation, so I mean right now I cannot explain because Sar hasn't taught it, and so you use this kernel and you do some operation on this input and you get some output using this. So again, it's a neural network, it's a function learner, and it will do some operation on the input that you're passing to it. And the difference here is that the output, the dimensions of the output will be different from the dimensions of the input. After you apply the kernel, after you do the convolution operation, the output that you're getting will be different than from your input. You'll do some calculations here. What calculations it is, I'm not going over right now. You'll do some calculations using this kernel and this image, and you'll get an output which is of a size smaller than your input. Typically it will be smaller. And there's another thing called stride, which is another parameter which dictates how you do this computation. Like how are you going to apply this kernel on this input? Like how, maybe there's a GIF that I can use. GIF. I'm not sure if GIFs work here. Yes. Right. No, maybe not this one. This one works. So you have a kernel. Here it's a kernel of size 3 by 3, and you're going to apply it at each position in the image. So this is how it usually works. And in this case, you saw that the image is moving one pixel at a time. So it first applied over these 9 pixels, and then it moved one to the right, and then it applied over these 9, and then it moved one to the right. So it's the step size is 1. That is called stride. So how many pixels is it skipping? It's called 1. It's called stride. So because in our case we have put it as 1, which means that it will first apply the filter over the first matrix, and then it will do one step, and then it will apply over the next matrix, and then so on. So in our case it is a 5 by 5 kernel. So imagine you have a 28 by 28. You have a 28 by 28 image, and then you also have a kernel of size 5, and then you are going to apply this kernel over your image with stride 1, which means that you apply it first over the first 5 by 5 matrix, and then over the next 5 by 5 matrix, and then over the next 5 by 5 matrix, and so on. Okay, so that's basically it. There's a lot of theory behind it of why this works, how it works, which hopefully we can do it in the next lab. And so let's make another convolutional layer 2D, which takes an input of size, which is just 10 channels. 10 channels means, so I don't know if you know what channels means. So in an image, usually it will be, so if you take an RGB image means a color image. If you take a color image, then it will be of shape 3 by say 28 by 28. Okay, and so there'll be 28 by 28 pixels, and corresponding to each pixel there'll be 3 values, which tells you how red, how green, and how blue it is. So it'll be 3 by 28 by 28. In our case, because it's a black and white image, it's a grayscale image, it's 1 by 28 by 28, because it's just one pixel telling you how dark it is. And you pass this through a convolutional network. So what will happen is I told you the input, the dimensions will change. So let's say we pass it through a convolutional layer, and the dimensions change from 28 by 28 to 24 by 24. But then this is not the only thing that will change. The number of channels will also change. The convolutional, so this is you can change this accordingly. So you can say it changes to 10 by 24 by 24 after you apply the first convolution, and then after you apply the second convolution, maybe this will decrease again. So let's say it goes to 18, and again this goes to 18, and you can choose to change the number of channels, or you can keep it same. This might become 20, it might remain the same. So that is how convolutions work. So that's basically how the data changes. The actual computations that's happening is not explained right here. So just understand that these are layers that do some kind of operations. The input is being modified. Some computations are happening on your data. The shape of your data is constantly changing after each of these operations. Yes. Sahil, do you have a question? Okay.
Sorry, my mic was.
Yeah. There are the other kind of there's another kind of layer called a pooling layer, which does another kind of operation. So these are all different kind of layers that are used in a convolutional neural network. There are not just convolutional layers, there are other layers, pooling layers, pool. So here we're using something called a maths pool. Say kernel size is 2. Stride in this case is 2. So I'm not gonna explain what the actual layers are. Just these are layers that are there. Right now we'll just see what happens when we train it, and then we can also have linear layers at the end so that you can then reshape your data for 4 by 4 by 10. And then we can have another fully connected layer that switches it from 100 to 10. Okay, so I have defined some layers for our model, and then we have to apply now we have to apply these layers to the input that you're going to pass to the model, and so that is what should be there in the forward, right? So finally it has to return something after you've done all the computations, all these computations that you've defined. After you've done all of this on your input, you have to return it finally, and that is the purpose of forward function. And you have to implement a forward function every time you inherit from an n-dot model. Whenever you're inheriting whenever you're implementing a neural network, you have to implement this forward function. And so let's do that. So first what happens, this forward function takes the self.conv1, it applies to x, and okay, and then it applies something called a solo. I don't think we've imported. Maybe not there. Maybe not there. So I'm just importing something else. Okay, somebody had a question. Yes.
Why didn't we do relu after every layer?
Yes.
Like,
Yes.
the one that
Yes. I'm doing it. That's why I imported the toaster function, and function, so that I can. Relu is an activation function, right? So. Yeah.
so we don't do it in the initialization, we do it in the final.
Initialization, so nothing is happening here, right? In the initialization, what is happening? We are declaring layers. We are not actually applying these layers. Where you can apply the layers inside the forward function. Oh, okay. So I think I understood why you asked that question, because we did an n.relu here. You can do that, or you can when you do n.relu, it's a layer. It's an actual layer, but if you use the n.functional, it's just a function. So it's the difference between a function and a class, right? So in toast.n.functional, so again, let's go to the docs. Toast.n.functional relu. So this, yeah. So toast.n.functional.relu is a function, and this function will take an input and it will give you an output on the spot. When you're declaring it as a layer. So when we made when you made the classifier earlier, you wrote n.relu. Here it's a so here you're instantiating the class, right? So here it's a layer. If we are implementing it as a layer, you can do that, or you can use the f.relu. And because the relu does not have any weights, right? There are no weights corresponding to the relu. What does a relu do? It's a fixed function. It's a fixed function, right? It just takes some input and it returns a predetermined output. Like there's no learning involved. There are no weights that you can adjust for the relu. So you can use a layer, or you can directly use toast.n.functional. So the toast.n.functional has a lot of functions like this that you can use. There will be a threshold function. There are other activation functions, elu. Softmax also you can, if you do not want. So if you want to apply your softmax as a function, you can use toast.n.functional.softmax instead of n.softmax, and so on. So like any kind of function that do not have weights will be implemented in n.function as well. Okay, so we took our input, we applied the convolution conv1 to it. You applied a relu, which is an activation function, to it. and then I applied the pooling function to it, and then I apply self.conv2 to it, and again I apply a relu, which is an activation function. You do not have to know what's happening, you're just doing a lot of computation on it. Self.pool again, okay, and then you reshape it, so then now it's let's say 4 by 4 by 10. So it's just flattening. Maybe after NetSlab, when you look over this, it will be much more clear. And then you apply fully connected one, and then you again apply relu. And you return it. Okay. So there are several layers that you declared. You're applying these layers one by one, and then you're also doing also applying the activation functions. So if you remember, I told you last time that you have to apply activation functions which are non-linearities. There will be sigmoid, tanh, relu. There are a lot of activation functions. You have to apply activation function because otherwise the combinations will just be linear. So if you apply like many layers one after the other, but you do not put a activation function in between them, then it is as effective as just applying one layer, because it will be similar to just doing one linear transformation. So you do not want that. You need your model to be able to learn non-linearity. So what you do is you have to use activation functions which add some kind of non-linearity to your model, and you apply that after each layer. So you did a conv1, you applied a relu, and then you did a conv2, you did a relu, and then you're doing fully connected, you did a relu, and then finally you do not have to do a relu, because finally after your last fully connected layer, your output is again of size 10. So you're again getting scores. You're getting scores in a tensor of size 10. Just that how you're getting it is different. How the actual what your model is doing is different. But then finally you're passing an input, you're getting an output which corresponds to 10, which will give you 10 numbers which correspond to each of the classes. Yes.
Yes, I wanted to ask that in previous implementation of
Yes.
classifier, we mentioned sequential.
Yes.
So rather than
we can use
mentioning
that.
sequential,
We can use that. But I mean, this is so you'll see both ways of doing it. You can do it this way or you can do it that way. You can also have implemented it as n.sequential. You could have had so you could have had a self.network or set.net, and you could have had a n.sequential here, and then you could have put each of these layers in here. You could have say conv2d, first apply a conv2d. You could have run this. You could have put all the layer models in here, and then you could have finally just done return self.net on its, applied on its without any of this. Just take the input, apply your network on its, and return it. That you could have done that. That is one way of doing it. This is another way of doing it. It's up to you. Yes. When you look at like implementations online, when you look at implementations, you'll see both ways being done. Usually I'd recommend doing this, but because then you can keep track of what is happening at each stage. Because like here, first you applied data relu. I mean, you applied conv1, and then you have the output now in ets, and whatever you want to do, whatever kind of analysis that you want to do, now you can do here. So you can say, okay, at this stage I want to know what is the shape. You cannot do that if you implement it as an n.sequential, right? So if when you're implementing it as an n.sequential, all of it will be happening internally. All of the stuff that you put here, it will happen internally, and you do not have any access to the internal computation. But if you want to do it step by step, that is also an option, which is why I did it different this time. Is that clear?
Okay, and one other thing that I wanted to ask is how we are mentioning the number of channels. Is it the first parameter that is there in conv2d?
Again, you can look at yes. So documentation says that first parameter is in channels, second parameter is out channels, third parameter is kernel size, and so on. There are a lot of parameters. Many of them are default parameters. So I mean, like there are default values for them. First channel is in channels. So when you're first passing your image, you'll just have one channel, and then you'll change it to 10 channels, and then you can keep. So maybe this could have been 32. You can change the number of channels after that. You can do lots of stuff. Like it's very flexible. You can do whatever you want. Maybe some stuff might work, some stuff might not work. It's all experimental. Like that's just, yeah.
Okay. Yeah.
Okay.
Thank you.
So we defined a CNN classifier. It's exactly the same as last time. Just that this time you have a CNN inside instead of a simple fully connected network. And this time a difference was that instead of implementing it as a n sequential, I just I'm explicitly doing each operation so that you can see what's happening. You can choose to do the other thing, you can choose to do this, it's up to you, like it's personal preference. Okay, so now you have your model ready. Now training data. So difference here is, in earlier we used to flatten the data and we do not have to do that here. So let's go back. Let's train set is fine. Let's do this again. So you have okay, but this time you do not need this dot view -1, 784, because you do not want to flatten your image such that it's 1/784. You're passing your 28/28 image as it is through your model. So you do not need that this time. I hope it's clear, because it's very important. When you're passing through an image through a convolutional neural network, you do not flatten it. You keep it as it is, as in a 28/28 image, and then you pass it through your model. Similarly, we also need validation. It's validation y, which will be here. Yes. And again, you do not need to reshape it to 784. You can keep it as it is. Okay, so one thing that I can do this time is, let's increase the number of training data that we're using. Let's say we're using 50,000 images. Okay, and let's say we have a validation set which is also bigger. Let's say it's 55. So let's say it's 5,000 images. 50 Okay, so now you have a training set which is 50,000 images, and you have a validation set which is 5,000 images. So last time we did training on CPU. So this time let's do it on a GPU so that it's faster, because otherwise we'll be wasting a lot of time. Okay, so what is the shape of your training data? So your training data, let's look at the first element of this. It's okay, that's not what I want to do. Let's look at the shape of this element. It's a 28/28 image. But when you're passing your image through a convolutional neural network, the data has to be in the form of number of channels times a number of channels, comma, width, comma, height, and batch index. So it has to be of this shape. Okay, so currently your training data, what is the shape of your training data? Shape of your training data is 50,000, which is the batch size, and 28,28, but then you're missing a dimension here which corresponds to number of channels. In this case we only have one channel, but then Con2D does not know that, your convolutional layer does not know that, so you have to implicitly put 1 here. So it has to be 50,000, 1, 28, 28, and for that there's a operation in PyTorch called unsqueeze. And what unsqueeze does is it keeps the data the same. It simply just adds a dimension somewhere, dimension where you're specifying. So you can say trainheads. So let's say torch trainheads is torch dot. This is operation called unsqueeze. And where do you want to add a dummy dimension? You want to add it at position 1. If you add it at 0, it will become 1, 50,000, 28, 28. That's not what you need. You want it to become 50,000, 1, 28, 28. So where do you want to add the like blank dimension? You want to add it at position 1. So you specify that 1 here. Okay, and let's also divide it by 255 so that it's normalized now. We did not do that. So let's look at the shape of trainheads now. So it will be 50,000, 1, 28 by 28. So now each image, so there are 50,000 1, 28, 28, images. So there'll be each image has one channel, 28 and 28, 28 length and 28 width. Yes.
Why have the images been made 1, 28, 28?
Okay, so earlier, what was your trainheads dot shape? Like what was the shape of your training data? It was 1,000. We were using batch size of 1,000, and we flattened each image so that it's of size 784, and we are passing through fully connected layers, right? In this time, what are you passing it to? You're passing it to a convolutional neural network, and a Con2D, the input to a Con2D, it expects the input to be of yes, the input. Look at this. The input. What is the input shape of the input that it expects? The shape of the input should be n, cn, hn, wn, which means it should be number of this is the batch size, comma, cn, number of channels, comma, hn, wn. So you're not passing images as 784 size tensors, you're passing it as 28 by 28 tensors. That is hn, wn will be here 28, 28. And then there's also an additional dimension called cn, which means channels. So in our case, there's just one channel because it's a grayscale image. But if you're working with, say, ImageNet or other data sets, then we'll have color images. We'll have color images, which is RGB data. And those will have 3 channels corresponding to red, green, and blue. And so in that case, it will be 50,000, 3, 28 by 28. It will not just be a 28 by 28 by 1 tensor. It will be a 28 by 28 by 3 tensor if it's a color image. But in our case, it's a black grayscale image, and so we only have one channel corresponding to a single color, right? Corresponding to how dark it is. So, but then Conv2D does not know that. Conv2D does not know it's a black and white image. But so you have to specify that in number of channels. Is that clear?
Yes. Thank you.
Okay. So first dimension corresponds to the batch size. Second dimension corresponds to the channels, and then length and width. Yes, Noah.
If we have a color image,
Yes.
how do we convert it to 3 dimensions?
You do not have to convert it to 3 dimensions. It will have 3 dimensions, right? If you so what?
Or the data itself will have
data
3.
itself. So when you are opening an image, as a tensor, it will automatically be of shape 3, say you have a 1024 by 768 image, an image which is of size 1024 by 768, and it's a color image. Say it's your picture.
Okay.
Then it will automatically, when you're loading that data, it will automatically be 3, 1024, 768, or 3, 768, 1024, however it's ordered.
Okay, thank you.
Right. In our case, we have a 28 by 28 image, but it has just one channel, which is a single channel. So that's why we have to add one here, because this is a space. So this is why you have to look at the documentation whenever you're doing anything, any function, any class. Just look at the documentation, and it's written here clearly that what the layer expects the input to the layer to be of what size, shape it expects it to be. So we have.
Excuse me, sir.
Yeah.
Yeah, what is the significance of unsqueeze? Can you explain again?
Unsqueeze. So let me run this again then. Train nets. So this part you understood how you are getting 50,000 images.
Yes.
Okay. So what will be the train x dot shape here? It will be 50,000, 28, 28. But then what does your Conv2D want? Your Conv2D wants a 4-dimensional tensor, or so here if you're doing batch, if you're using a batch, then there will be this dimension anyway. This n corresponds to 50,000 here, and then there's also an additional dimension here called cn. And what is the cn? The cn corresponds to channels, and that is why. So we have to add this one extra dimension here. So this dimension does not have any purpose in terms of the actual data, but then your Conv2D is implemented such that it will only take data of this shape. So you want to convert this 3-dimensional tensor to a 4-dimensional tensor, and you want to add an empty dimension. Where do you want to add it? You want to add it at dimension 1, and that is why what toss.unsqueeze does.
Okay.
Again, you can look at the documentation. This is why I stress that you have to look at the documentation. Unsqueeze torch.tensor.unsqueeze, yes. So it returns a new tensor with a dimension of size 1 inserted at the specific position. That's all that it does. So there's similar to torch.unsqueeze, there's a function called torch.squeeze as well. So what that does is, if you take this data and you want to remove this single dimension here, then you can do torch.squeeze on trainers, and if you say remove this dimension, then it will just squeeze out. It will squeeze out this empty dimension. If you want to squeeze in the opposite of squeeze out is unsqueeze, and that is why it's called unsqueeze. So yeah. So you have your trainers, and then you also have your validation data set, and then you want to unsqueeze it so that now it's in the shape that your convolutional network is expecting. And similarly, you also want to do this for your validation. It's
Okay.
yes. Okay. So you have so now the shape of your validation will be what? It'll be uh, it will be 5000 comma 1 comma 28 comma 28 because there are 5000 validation images. So now you have your training set, your validation set, and let's load it into the GPU. So you can do trainers CUDA validation as validation it's dot CUDA. Okay. So now your training data is in your GPU. You have to do that as whenever you are training a model on GPU. You have to load your data to the GPU. You have to load your model to the GPU. Yeah, that's pretty much it. Okay. So now we have your training set, validation set. Now let's make our model. So model is what? This time it's a CNN classifier. Okay, and this time we have to load it to the GPU as well. Okay, so now you have your model. You have your data. What else do you need? You need a loss. Loss will be again cross entropy loss, and optimizer again. You can use same thing. NN dot. It's not an NN. It's an optim dot SGD. Model dot parameters and learning rate, let's keep it as 0.01 only, I guess. And then batch size, this time let's say batch size is 100, and let's say we are training it for, let's not train it for 200 epochs. This will be overkill. Let's just train for 10 epochs, because now the data is 50,000. There are 50,000 images, and so you're in each epoch your model is seeing 50,000 images. So it's not necessary to train for that much. Let's just train for 10 epochs for now. Everything else is same. Let's just copy paste it from here. So you have a number of batches per train epoch. Exactly the same thing. In this case, it will be what? In this case, number of batches per train epoch will be 500, because you have 50,000 images and each batch has 100 images. So it will be fine. There will be 500 batches per epoch. Okay, that's clear. Then you can train your model, and for that you can copy paste this entire training loop that we wrote. There'll be some differences somewhere. There should be, because now we are training it on a GPU, so you have to be careful about that. Okay, let me see, what do we change? So everything else is the same. You're passing it to your model. This is fine, and then maybe evaluating. You are right. So here, what you have to do is you will have to detach it. So detach dot. Let's call CP on it. Okay, so now wait, I'll explain this in a bit. Let me just write it for this as well. Detach. Okay, what's wrong here? Oh, okay. Did I put an extra bracket? No, I put a. Oh, okay. All right. Okay, it's fine now. So your predictions, you passed your model stuff through your model. You got your outputs. You also have your predictions, and both of them are on your GPU. But then, so what detach does is it detaches your it from the computation graph, so that yeah, so that gradients are not calculated for it. And then dot CPU, what that does is, so right now your train predictions and your train targets are on your GPU, because all these computations is being done on the GPU. So in order to add it to a list, you first have to so you can't convert a tensor that's on the GPU to a numpy array. If you want to convert it to a numpy array, first take the GPU out, take it from the GPU memory. First take it out from the GPU memory. So how do you do that? You do dot CPU. So when you do dot CPU, and then you can do dot numpy. That should be the only difference as far as I can tell. Yeah, same thing you have to do it here as well. Yeah, right here as well, and here as well. I can't think of any other differences that might be there. Let's see. Right, so here loss of TG-Pog. I think we were supposed to detach it last time as well, but it's fine. I think this is pretty much it. Let's try running it. If there's any error, we can deal with it then. Okay. Expected all tensors to be on the same device, but at least okay. Where are they saying that? When we are calculating the loss and loss, we are calculating here, and the problem here is that let's see what the problem is. They're saying that output and targets are not on the same device, which is weird because wait, let's see what's happening. Okay. Okay, so that's the problem. Train Y, we have not put our where the hell did we do it? Yes, here. Okay. So the problem was our train Y and our validation Y, we did not put it on the GPU. Yes, that's all. I think that should work. Train Y, CUDA, and then your validation Y. This validation Y dot. So now this should be on the GPU, and now it shouldn't throw an error. Hopefully. Oh, okay. I had a print function somewhere. Let's see what's the problem is. Print. Where did I put a print? No, not that. Oh, okay. So I had put a print function here. Let's remove that. Lol. Let's. Okay, now so let's run it again. And it's not working because the loss is the same. Let's see what happened. Let's see. Optimizer. And you took the. This is correct. And then you calculated the batch loss. Did we remake the loss? We did make the loss again. Then we. Did I put model.train? Yes, model.train is there. It's printing velocity GPOC and just give me a few minutes to figure out what's going wrong. Switched it to val. Oh no, it's not that. Okay. I thought I got it figured out, but no, it's not that. Okay, let's see. Let's rerun this stuff. Maybe something else. I made a new model. The training data also is validation. We loaded it on. We normalized it. We loaded it onto the GPU, and we made a model. We made the loss, which is correct, and the optimizer is also correct as far as I can tell. Yes, batch size is 100. Is this correct? This is also correct. Train by devices, now it should be GPU. See, look, yeah, it's CUDA. Let's see, epoch. Switch it to train mode. If anybody has any idea what's going on, please tell me. Optimizer. Very weird. I'm not sure. Oh, okay. What the hell? Okay, somehow it's working now. I'm not sure what I changed, but maybe because I forgot to run one of these in the middle. Maybe I was using the loss from last time or something. Probably that. I'm not sure. So it's training right now, and the loss is decreasing, so that's good. The accuracy is also great. Okay, so wait, how many epochs are we trying for?
What had been the problem?
I'm not sure. I think it might have been that I forgot to, like, I wrote one of these like maybe I did not run the loss, or maybe the optimizer. I'm not sure because it was in training, right? Because the loss were remaining constant, which meant that the optimizer was not updating the weights, which meant that I might not have run this cell here, right here. This cell I might have forgotten to run it. I'm not sure. It might have been that. Why is it training for more than 100? Okay, why is it training for more than 10 epochs is what I want to know now. Number of epochs. Okay. It should have been epoch here, but you get the point, right? It works. Why did I name it epoch though? It's number of epochs, so that's same as last time. Epochs. Everything else is the same. So let's run it again because I only wanted to train it on 10 data, 10 epochs, because otherwise it'll overfit to the data. That's what the hell? Right. Cool, it's working now. So you can see the training accuracy is increasing, validation accuracy is increasing, loss is decreasing. So it's good thing, and I'll only train for 10 epochs, and we can do the same thing. We can look at the graph for this as well. Yes, it's pretty much. I mean, the training and validation accuracy is pretty much the same, which is fine. So this time you can see that accuracy is higher. If you trained it for a bit more, you saw that it went to 98 earlier, which is higher than what you got with your fully connected network. So convolutional networks are inherently, like, they have certain properties that make them much better for image data, and so and you can see that with the accuracy as well. Just after like a few epochs, like, the accuracy, I mean, yes, it is seeing more data right here. Plus we are also training it on a GPU, so that might be why it looks faster. So it's pretty much it, I think. I don't think there's anything else. Let's see. Oh yeah, so there's one other thing. That I was thinking, which was that so I saw slicing the feature maps. So I saw a Medium post by some dude, Ravi something. Yeah. Sahil, yes.
Please, could you repeat the last few lines? Why convolutional networks have some special features? My light went off. Sorry.
There are many properties of convolutional neural networks that make them much better for image data. And what those properties actually are, hopefully sir will cover in the class. Hopefully. But then I'm just saying that you can see from the accuracy itself that it's performing better on the both the training and the validation data. That is just an observation I made. There's nothing else.
Nothing though.
Okay.
Thank you.
Cool. So we have trained a simple network. We have trained a convolutional neural network also. What's actually happening inside it has not been covered, but then you got a feel of how you pass data to a convolutional neural network, how you pass data to a simple fully connected network, how you calculate the loss, how you write a training loop. Like what all did we do in the training loop? We actually trained it. We reported the accuracy on the training data. We reported the accuracy on the validation data, and you did that after each epoch, and you printed out the loss and accuracy and everything after each epoch. You do not necessarily have to do it after each epoch. If you're like training it for 1,000 epochs, then it does not make sense to print it after every epoch. You can maybe add a if condition here, saying that if it's a multiple of 10, every after 10 epochs, print all this information after every 10 epochs. You can do that. It's up to you. So yeah, so what I was saying was I saw this Medium post which helps you to visualize your. So the actual code is not important. I just want to use it so that you can see what's happening. Okay, let's just copy paste this. The actual code is not important, but then the actual what you see, what the result is, what's important. Let's just copy paste it. Because here also he has named it as model, I think. So it doesn't. Or did he not? Yes. So he called it model as well, which is why it's running. And then it's already on GPU. That's fine. You do not have to transform it. And let's pass an image through the model. So let's name an image as train. Let's take the first image. And what is the trains.shape? Trains.shape will be 1 by 28. Oh, okay. Lol. Not trains. Image.shape. It'll be 1 by 28 by 28. And then let's copy paste this. The actual code is not important. Like you can look over it if you want. It's pretty simple. What he's doing is he's applying each convolutional layer one by one, and he's keeping track of the output, and then he's visualizing it. It's not important. You can look over it if you want because the Colab notebook will be shared. The point is you can see what's happening. We do not want to save the figure either. Right. Okay. So I think so. This is the output of after the first convolution, and this is the output after second convolution. And our model is pretty small. Like there's only 2 convolutions, so you can't really tell what's going on. But then if you just for the purpose of illustration, let's just look at a different model. We're not going to train the model or anything. We'll just take a pre-trained model and then we'll just see visualize what the output is after each epoch, so you can get a feel for it. So let's use a model called ResNet. We'll choose ResNet 18. It's not important. And ResNet 18. And then what do they need? They need weights, I think. And then we'll use let me just look at I'm not sure about Torch Vision. ResNet 18 models. ResNet 18. Nope. Wait. Okay, so this is the weights. Okay, right. So we want this one. ImageNet 1K underscore V1. ImageNet 1K underscore V1. So basically what's happening is I'm just using a pre-trained model, a model called ResNet 18. So similar to how we used a convolutional network here, it's a convolutional network based model called ResNet. And so I'm using weights of the model that are already trained. Like, so the model has already been trained on a dataset called the ImageNet. And I'm just using it so that we can visualize what's happening. Okay, so let's do the exact same thing. Let's just, so that we can see what the output is after each layer. We need an image. So it's ImageNet sample image. Let's just take a sample image. Any image, it doesn't matter. Let's take. Let's look at a picture of koala. Okay, that's too wide. Something that will be easy to visualize. I don't remember what I used before. Like I had done this before, so like I took a picture of a dog. So let's just take a picture of a dog then. I hope this is a dog. Yes. Okay. Let's take this. Yeah, that works. Let's just download it here. I hope it's the image that downloaded. Let's just see. Nope. Yeah, this is what we want. Right. Okay. So now I have an image that I've downloaded. I will open it. For that, I will use the library. So that none of this is important. I'm just doing it so that you can get an idea of how the features look like after you have. I'll apply that to my image. I will normalize it because I think you have to normalize it. And this 0. So what I'm actually doing here is not important. We'll do that in the next class. But then I'm just opening an image and I'm normalizing it. And now I'm going to pass it to the to a pre-trained model so that then we can visualize what the output after each layer is. What did I do? Torture and squeeze argument must be tensor. This is not a tensor. Why? Ah. Oh. God damn it. Okay. Right. Okay, now we have an image and now we can do the exact same thing that we did before. We can pass it through all this stuff. Outputs. Where did I copy it? Then great. Hopefully you can see the output after each layer. So like we start out with a dog. And then after the first convolutional after you apply the first convolutional layer, this is the output. And then like after successful convolutional layer, like various kinds of computation is done on the feature maps. Eventually the resolution of the feature maps becomes lower and lower because you're, and then finally, so I mean you can't visualize, I mean using I mean you can't understand what this means, but then there'll be some significance to this. So finally, after you apply a fully connected network to like predict what the label corresponding to this dog is, so then there'll be like something that happens with the fully connected networks. So it'll make use of this feature. This is the output of the last convolutional network. It'll make use of this feature, and then it'll decide whether it's the specific kind of dog or what kind of dog it is. Yeah, so that's just it. So I just wanted to show what the output after each feature, after each convolution layer looks like. It's not important. Like the actual code of what is happening here is not important. There's this medium post that you can look at if you want to. It's not important though. The important thing is that we have made a neural network. I mean, we've made a convolutional neural network. We've trained it on MNIST, and we have reported the accuracies and the losses after each epoch and also after the entire training is done. I think that's pretty much enough for today. Like next time we'll actually look in detail at all of this, like what exactly is happening within a convolution, how how should we decide how many convolutions to use, and all this information, like how do we apply it to certain kind of problems, like maybe you want to detect images within a detect objects within an image. All of this we'll cover in the next lab. So that's pretty much it for today. Collab docs. So if you go to the website for the course, then if you go to lab sessions here, so sir is putting the link to the, so this time I think it was a bit late, but then next time onwards I think it should be available immediately. So the video and the collab notebook is available here. So like if you don't get, like if it's not uploaded within a few days, just email me. Like a couple of people were emailing me this time as well. I'll just send it to you if you want.
Good afternoon, sir.
Yeah. Yep.
So I have a request, sir. Like before you start the lab, if you could share the collab notebook that keeps on getting updated simultaneously, and we can also like take a look at it.
Okay, that works. Next time I'll do that.
Thank you so much.
Yeah. Okay, so now we have the quiz. I forgot about the quiz. Let me stop recording.